Hey guys, my name is Lenny Meestar, and I'm part of SimpleSoft. We're in the ECE480 project, which is software engineering at Cal Poly Pomona. And for our project, we decided to build it to build a real life application of the paper presented to us by Dr. Yin and Andrew Chan, which is a real-time maintenance and maintenance prioritization with learning capability paper. This can be found in the IEEE website. And just a quick overview of our system. I'd like to show if this can work with me here. So an overall architecture of our systems. We have the main components, which is a web app, which is running Bootstrap, AngularJS, and is being hosted on GitHub Pages. And our main target will be some sort of an engineer or someone who's on the technical side, obviously. Now we built an API using API Gateway, which hits AWS Lambda that updates the status of our IoT. That's our essentially our messaging hub. We have a slow brain and a fast brain. That's according to the paper. Our slow brain we're using also an AWS Lambda, written in Java. Our fast brain is running Python, which is running a script that's always listening to event changes from IoT. We have Alexa, which we integrated to ask the ask it about the status of our system, and obviously we have LEDs that are representing subsystems and the system overall of our system. So this is the overall architecture, and let me give you guys a demo. Just a quick thing I'd like to point out. This is our system. This is how we modeled. So as you see, we have P0 through P7. That's 8 subsystems within the system overall. These 8 subsystems are being represented with these LEDs. So P0 through P7. And here we have the health status of the system overall. So currently everything is good. So it's green. And if any of these ones in parallel changes, it'll be a yellow. So not, the system is still running, but you might want to consider fixing it. And if it's red, that means any of the series line are turned off. That means you need to go ahead and fix that as soon as possible. So let's go ahead and demo this now that you guys saw the system overall. We built this UI. With this UI, you can actually interact with our system because we're delivering a platform as a service. So let me go ahead and run the. This is I'm SSHing into the Raspberry Pi. Currently, everything is on. So went ahead and it started learning. So went ahead and asked the slow brain, and it took it 0.8 seconds in order, and it's telling me to fix none. Now, if I go ahead and fix, turn off, let's say, a series one, which is a P5, right? And then I go ahead and submit that. Now, if you notice that the LED here turned red, this LED turned off, and in the terminal, which is we're looking at what the Raspberry Pi is doing, it's telling us to fix P5. Actually took it 0.3 seconds, and it went ahead and asked the slow brain. Now, it asked the slow brain because it never went through this state before. Now, if, let's say, for example, let's break some of the parallel ones. So let's say we fix P5, and we say we broke P6. Now, let's say we broke P6 and P1. Now, we saw that 2 LEDs turned off. Now we have a yellow light, and it's telling us to fix P6 because the mean time before failure for P6 is higher than the mean time before failure of P1, for example. Now, let's say we fixed those issues, and P5 went out one more time. So that means we're going through a state that we went through before. And for the fast brain, it went ahead and asked for the fast brain this time because it went through it before, and it took it, it told us, to fix P5. Now it took it 0.00126 seconds in order for it to fix this issue. Now, we can keep going and fix any of these, and for example, we say now P5 and P3 broke. And it's still telling us P5 because P5 has a higher mean time before failure, but this time we went ahead and asked the slow brain, and it took it 0.31 seconds. And that's it. Thank you for watching.